Hi, everyone. We're talking about driving stepper motors. When we left off, we had this code here. We called it stepper 2023, part 2. We are sequentially driving these three axes, the Z, here the Y, then the X. That's what we're calling them using these steppers. We're controlling the speed. We're running it kind of a bang control, a constant linear speed, but that speed is reversing, and we're running the steppers sequentially. You can see here we had the kind of the layout of our layout for our three steppers: the Z, the Y, the X axis on the corresponding ports. Setting up those ports as appropriately as outputs. We had a time delay between steps. These are in microseconds, and we would define the number of steps. We right now our drivers are configured to run in half stepping mode, or 400 steps per revolution. So if we're running right now 2,000 steps, that gives us 5 revolutions of each of these axes. Here sequentially we're running first the Z axis through those 2,000 steps, then the Y through those 2,000 steps, and the X through the 2,000 steps. We mentioned that we're running these standard stepper motors on the DM556N stepper driver, and I mentioned a few words about it. For what it's worth, we can very briefly look at the drive. A picture, here's the drive. It is a micro stepping drive, so you can see you can choose all these options. The default is full stepping or 200 steps per revolution. You can choose 400 steps, 800 steps per revolution, and so on. We're running this half step mode, so you would just correspondingly set these dip switches. You can set a max current you would allow to go to your steppers if you want to avoid overheating. Of course, the current's a function of the winding, the voltage, and then the winding resistance. However, you can limit, this driver will limit that maximum. There's some smoothing filters and a few other things, some auto tuning and alarms. I had mentioned very briefly on the values that we drive it, and it requires a minimum pulse width of 2.5 microseconds. I think we were using 5 microseconds. I'd said 5 microseconds. The 5 microseconds, it requires a minimum of 5 microseconds between a direction change and then the next pulse to actually see that direction change. And you can see that down here in their little table. So they show, here's your pulse. And by the way, it captures on a falling edge. So if you change the direction, a falling edge on your direction line, then it's not going to register that direction change until you get the next falling step. So it would be a good idea if we put a 5 microsecond delay between our direction change and the pulse, for what it's worth. And then they're saying they want a minimum of a 2.5 microsecond delay on the steps. All right, so that's a kind of an overview of the driver that we're using. And again, here's our code. So our next step would be here we're running sequential motion in this linear, kind of a bang linear velocity control. The next thing that I want to review is how would we go about driving these sequentially? How would we run these steppers sequentially? And we're going to review that now. To do that, we're going to change the way we're thinking about driving these steppers. So let's first, we're going to write some code. So I'm going to work from this code, but I'm going to save it now as our part 3. I guess I could call it, I'll leave it as part 3, but up here I might add the part 3 is sequential drive of steppers. Sequence. I guess I'm doing sequential. I guess I want to say simultaneous or contemporaneous drive of steppers. And what's going to be unique is we're going to now embed this in a real-time interrupt. So we're going to introduce the concept of real-time interrupt. So work from this. To do that, let's jump back over and quickly review our real-time interrupt. And we had discussed that on the app Mega, there's a lot of options for interrupts and real-time interrupts, but one that I'm going to turn us to immediately is to use the timer overflows as real-time interrupts. we have 6 of those. We have 2 8-bit real-time interrupts and then 4 16-bit real-time interrupts. We will, these real-time interrupts will occur on overflows of the corresponding timers. When we scroll down, we can look and see what type of capability we can get. And here we can see for the 8-bit overflows, we can get overflows that would occur and then the corresponding interrupt that would occur here at, if I talk in milliseconds, this would be like 0.016 milliseconds and so on. If I look at the 16-bit, this would start at 4 milliseconds and then so on. Now, what kind of time do we want? If we jump back over and look at the code, right now we're running, if you recall, we played a little with this bit with the speed, and we found that 500, a delay of 500 microseconds, or if you will, every step would occur once every 500 microseconds. That seemed to be about the maximum we could get with this bang bang or full blot, starting from 0 to max velocity. That's about the best we could get with a simplistic bang bang max acceleration control. Really, we're expecting an infinite acceleration. So 500 microseconds is the shortest that we can get. Again, when we put in a smaller number, we definitely saw that we were losing pulses. Now we could slow it down. So if we use this concept of 500 microseconds or half a millisecond, and then look at our options, well, with a 16-bit overflow, right off the bat, we start with 4 milliseconds. That's, quite a bit higher than half a millisecond. I guess I'd like to see at a minimum 1 millisecond, but the 16-bit overflow, I could start at 4 milliseconds. So based on that, I'm going to jump over here to the 8-bit timer overflow interrupt, because I can, with a 64-bit prescaler, I could get down to that 1 millisecond interrupt period. And I could drop it down to a quarter of a millisecond or an eighth of a millisecond, or down here to way less than that. Again, 0.016 seconds, milliseconds per interrupt. So I'm going to choose to use the 8-bit timer overflow, real-time overflow. And to do that, I come down here on the, so I'm going to use it on the 8-bit timer. I have 2 of those. I have timer number 2 and timer 0 and timer 2. Now this registration is for the 16-bit timers, but it's pretty comparable. So I'm going to either use timer 0 or timer 2, the two timers. I do not care about these compare output matches in terms of weight, so I'll leave them 0 for normal port operation. I'll be in wave generation mode 0, also for the 8-bit timer. So this register is going to be all zeros. Timer control register B for either timer 0 or 2. I'm not going to worry about the input capture noise channelers. Again, my wave generation mode is going to be 0. I'll put all these zeros. And then finally, I have to select my prescale. I have to select a corresponding prescale. And then the very last thing I have to do is to turn on the timer flow interrupt. I need to go and turn on the interrupt. And that is in this timer counter interrupt mask register. We're going to do it for channel 0 for the 8-bit timer, and we will enable the timer overflow interrupt right there. There's one other little step, which is it would be nice to clear the timer overflow flag when we first start it, just to make everything start from scratch. Okay. So that's what we're going to set up to do. So we're going to come over to our code. We're going to make some pretty significant changes, but let's step through our changes. The very first change I'm going to do is, well, I guess we can do one thing at a time, but let's turn off at the moment. We're going to turn off or actually eliminate the sequential motion. And we're going to come back, I guess, even and we're even going to get rid of this. So, oops, we're either going to get rid of this guy. So effectively, we're going to turn everything off. Because we're going to run in the real-time interrupt. We're not going to run anything in the, we're not going to run anything really in the loop unless we want to just do some other activities like print out. I'm going to turn that off. So I need to set up my, my IO for pulse or step, step pulse. call it step pulse because they call it pulse and direction. And I did that here. Lost my mouse. Here I'm setting up my initial variables. Variables I'm going to use. And then finally, I'm going to, I need to set up my timer. So we decided that we're going to either use, so we're going to, as a few notes to us, we're going to use either a timer 0 or 2 8-bit timers. We're going to turn on the timer overflow interrupt. Timer overflow is TOV interrupt. And then in terms of prescale, I guess we could jump back and look at our prescale. In terms of the prescale, we could choose different values. Again, we're running right now half a millisecond. So, you know, we could run a prescale of 16 to give us a little more wiggle room. Let's run a prescale of 8. Okay, so we're going to run a prescale of 8 or 0.128 milliseconds. So we're going to run a prescale of 8. It's a clock prescale of 8 to give a 0.0000128 seconds between each timer overflow interrupt. Okay. Now there's a quick note, and this just discover this every year for whatever reason on this Arduino timer 0 overflow vector, however it's pronounced, does not work. I don't know why. I keep reminding myself, I keep using it and it doesn't work. Something to do with, I guess for some reason Arduino has used that. It's probably documented somewhere, I haven't found it. So based on that, we're going to use timer 2 overflow vector. And we can look it up in that jump table to see the exact name, and I have it jotted down here, so we'll go with you. So the first thing we need to do is set up timer control register. So we're going to set up timer counter control register 2A, and we're going to do zeros for the, see, that would be output compare A, output compare B, output compare C, and then the wave generation mode. So we're going to be in wave generation mode 0, which is normal port operation. And then we're going to go to timer control register 2B, and we'll be 0 0 0, and then for the clock prescale. So if you jump over to your notes and look, we're still going to be wave generation mode 0 for normal port operation, and our clock prescale, I think they call it CS2 to 0. CS2 to 0 will be 0 1 0 for a prescale of 8, giving us that 0.0000128 seconds. And then finally, we're going to set the timer interrupt mask register. So timer interrupt mask for timer 2. We're going to enable it, and that's the least significant bit. So we're going to enable the timer overflow interrupt. And then I'm going to, we had it in the notes here. I want to reset that flag, set that flag to 0. So TIFR, timer counter interrupt flag register, TIFR. So TIFR, panel 0, just line everything up, 0B, 0, 0. So this is going to reset the timer flag. And I think that was, I'm going to double check to make sure that was on the, oops. Yeah, and that was the least significant bit. Okay, So now now our timer is all set up. In case I need it, I'm going to go ahead and I'm going to turn on the serial just in case I decide to use it. So I'm going to turn it on. So I'll turn on ready to the serial on. Now, to do this, to create this timer, or excuse me, this timer overflow interrupt service routine, I've now turned it on. It's going to run. So every time that there's a timer overflow, the AtMega hardware will generate an interrupt. A couple things will happen in that interrupt. It's going to set the flag, which we've reset here one time, and it can also issue call and interrupt service routine. So we're going to create that. So we'll go down below. We're going to create our interrupt service routine for timer to overflow interrupt. The code for that looks like this. We call the timer up. We declare it by issuing this command for the jump vector, and it's going to be timer to overflow. I did that wrong on my C vector. I think that's in the notes. I think it's timer overflow like 20. You could put that in as well. And this is going to be my interrupt service routine. So whatever code I want to occur on this is going to occur. Now, this is a function. It looks like a function, or we'll call it an interrupt service routine outside of setup and loop. So any variables that I want to use in here, I'm going to need to make, either going to have to pass stuff around as pointers. I don't know how to do that in interrupt service routines. So what I'm going to do is create these as global variables. And I guess there's two variables I want to create. One is going to be a count variable, which we already have. I've got this number of steps, which honestly, I guess we can still use, and let's go ahead and use a time. I've got that DT, but that's not going to really make sense the way I've got it here. I'm going to make a time variable as well, but for time, I need something that's a float. So I'm going to create a time variable and initialize it. Now I need to do one other thing. It's in my mind. I could issue a pulse, a step pulse on every interrupt occurrence. However, that's a little faster than I wanted. So I'm going to have one counter for the number of pulses per step, and then I'm going to have another counter for the the number of steps I have before I change directions. So let's make them. I'm going to count. We're going to call it count ISR per step. So I'll make that guy, and then I'm going to have a count just for num steps. Okay, a little confusing. So, and I guess we're not going to, in my way I'm not going to use this DT. So I'm going to get rid of that. So, actually, when I was thinking about count number of this count ISRs per step, really what that's going to determine is that's going to determine our speed. But I guess we'll call it here count ISR per step is the is number of counts to generate a step, or number of what actually is going to be number of the interrupt service real-time interrupts overflows. It's going to be the real-time interrupt timer overflows per step. That's what that guy's going to be. The count number steps. It's going to be the number of steps. between direction changes. It's just a count for that, and then the number of steps is actually the number of steps. Okay. So, and then there's a direction, may or may not be clear, and we got to initialize these. So count ISR per step. We got our direction, and then we don't need DT. I've already declared that, but I guess I can get rid of that whole thing. And then the count of steps, 0, and then the number of steps. Now this one's going to be, yeah, I guess the number of steps will work. Okay. So I think we've got it. It's probably clear as mud to you, but bear with me. We'll hang along. Okay, so now that I've got these variables, I'm ready to jump down to my interrupt service routine. So the first thing I'm going to do is create a update my time. So my current time is going to be my previous time plus the time per step. And we said that that was, since we used that, eight prescaler. So we're going to get 2.8 seconds per timer overflow for prescale of 8. Okay, we've got that. We're going to do our count. What do we call it? Count ISR step. So we got to index that every time. So I think we can just say plus plus. We're just indexing this rascal. And I think that's all we need to do there. Now, first thing we're going to do then is say if the so basically this counter that we have, count ISR per step, is greater than, well, however many steps that we want. I should have just called this counter, but however many steps we want to occur. With this 0, 1, 2, 8, we wanted about, we said we need about one millisecond. So it seems like a factor of 10. Let's try a number like, let's try a slightly larger number to start with. So we'll use 25. So for every 25 of these interrupts, we're going to make a step. Now, to make the step, I'm going to do two things. First, I'm going to set the direction. And I'm going to set the direction with this. I'm going to, I haven't quite been using it, but I'm going to start using it now. Or equals, this is a little bit hard to unwind, and I'll do this another time. You know, or equal, it's a method I found where I can specifically set these steps according to defining the current direction. So it's negative dir, exclusively ORed with port B to begin with, and then I'm going to AND that with the bit that I want to set. So it's going to be 0B 1 0 0 0 0 0 0. So there I'm setting the direction for PB7, which is z-axis. Okay, then I realized that we have not been doing this, but I set that direction. I wanted a microsecond delay. I've not been doing it, so let's come back and add it later, but we're going to need to do that. Next, I'm going to send pulse, step pulse. And so we've got port B, and I missed my port B above. We get port B. I'm going to and equal it with 0B for the binary value. I've got to set it now on PB6. So I'm first going to set the bit low. So I'm going to and equal with a 0 in that PB6 location. So I'm set PB6 low. This is the Z-axis. I'm going to do my delay microseconds. And it said we needed 2.5 microseconds to delay, but we'll do 5. And then I'm going to set the bit high. So to set PB6 high, I'm going to or equal with the mask 0B 01 00. Okay, so that sets set PB6 high. It's the Z-axis. And then I'm going to update, I'm going to reset my count. That's a long name. Would you guys allow me to just go back and just call that count CNT? Humor me on this. I don't like that name as our step. I think it's just confusing. Let's call it count. So we're going to set that back to 0 so it can start counting up again. And then I got to go back up above and reset it. And then our count number of steps, let's at the moment leave that. That's the number of steps I'm going to make. I've got to index my count number of steps. Count steps equal plus plus. So I've indexed the count number of steps. So I've forgot to open and close my braces, and this is closing my timer. So here we go. Every time the timer overflow vector occurs, I update my current time. Just if I want to run and count on time, I update the count. Once I get 25 of these counts, at this point I'm choosing this number 25, I'll actually send a pulse. That's just based on the time per count. So I got 25 times this many seconds between pulse. I set the direction. I should do a little 5 millisecond delay, but I'm not doing it at the moment. I set the bit low, wait 5 microseconds, set it high. Setting it low sends the pulse. That's what makes a step. I set it back high and then leave it there. I reset my count so I can get 25 more counts before the next one, and I update the count number of steps. The last thing I would like to do inside this register is determine if I need a direction change. So I'm going to put it here. If I for a direction change, I'm going to check my count number of steps. So let's say check for a direction change, or when we're going to change direction. So I'm going to say if count number of steps is greater than that variable we call num steps. We're going to do a direction change. So dir equals the inverse of dir. And I'm going to reset my count number of steps. And that's it. Okay, let's go up and check a couple things. So we got count number of steps, num steps, and count. We've got those things. Num steps is 2000. I'm going to cut that down to just one rotation to start with. Okay, I think we're ready to give this thing a try. And notice there's nothing in loop at the moment. We could put something in there if we wanted. I suppose we could print out the time to the screen. Although I'm going to probably ignore it if we just want to track time. So let's give this a try. So I've got this count, ISR not declared, and scope. Because I made that 0. Too many closing braces. Holly. So we only turned on the Z axis. Um, but we can see it running there. And so, and then also if we wanted to watch what's happening in terms of the serial monitor, every time I open the serial monitor, I see it restarts. So it's printing the current time to the screen. It will say that that time does not seem to be accurate in any possible way, but that's something we'll need to chase down. Am I off by a factor of 10? Ah, yes, I'm off by a factor of 10. That's why. Let's go back and fix this. Too many zeros there. Recompile. Okay, so it seems like that time is approximately correct. Just giving a running a time, but that's all that's happening in loop. So all my motor controls happening, it's interrupt service routine, which occurs once every 0.128 milliseconds. And I'm driving the Z axis. I'm controlling the speed here with this number. So let's change that variable to speed. I'm going to go up here and make this variable into a speed. And then down here, I'm going to define the speed as, I need a number. At the moment it's 25, but what is that thing actually? Well, this is the speed of the stepper, and it's going to look something like this. What's it going to look like? Let's see. Speed is in units of timer clock cycles per step, or it's going to be, and the number of clock cycles here are going to be the speed times our speed of our clock, which is 0.0625 microseconds, times 256. It's we're running an 8-bit timer overflow, times the prescale, which in our case was 8 per step. So if you put all that together, that's the speed per step. That's what we're running right now. Fairly slow, but it seems pretty reasonable. So if you're happy with that, and then also we could run a few more steps. How many steps are we running? We're running 1 rotation. Let's make that be 2 rotations. Or we could, let's even make it 2.5 rotations. Okay. So this is in our setup. We're defining these, and on the actual machine, there's the consistent problem we've been having of on startup, we're sort of dumb as we started, but there we go. So now we're running 2.5 rotations on each. Got it. Now, we haven't done what we set out to do yet. The goal was to do a simultaneous drive of the steppers. But look, we are now able to do that. We've freed ourselves of the for loop, which forced a sequential drive. We could actually get rid of all this stuff. We freed ourselves of all this. So I'm even going to delete it. This is all there is in void. And we've put everything in the overflow. So let's go ahead now and drive 2 axes at the same time. So the first thing we need to do is set direction for the Z and Y axes. Here we're doing exclusive OR, port B exclusive OR with, first of all, the direction exclusive OR with B. So that sets our direction. And then we're going to set that for PB7 and PB5, which is our, I believe, our Y axis. Then we have to send our step pulse. First, we set it low. There we set it low for the PB6. Here, let's go ahead and set it low for PB4. Oops. So I'm set PV4 low, which is our y-axis. We'll do our delay 5 milliseconds. So now we're pulsing both one and then the other one with 1/16, approximately 1/16 millionth of a second between them. We'll delay our 5 microseconds, then we'll set them high. So there is PB6. Now I've got to set PB5 high. So or equal with 0B, 0, 0, PB5, a 1 there, 4, 3, 2, 1, 0. So I set PB5 high, which is our y-axis, and everything else is fine. And now the only issue is I'm just driving the both of them the same amount. Later on, we'll think about driving at different amounts, but let's first look at simultaneous driving. So I'm sending this code off, and it's not working. Take a look here. Just a moment here. So, not quite sure what I did differently there. Let's pull it back over and look. Oops. Okay, it's gonna be unhappy with me. Back over. Set one of these ports incorrectly set. Sure, not really sure what's different from what I did a second ago. I just retype them. Okay. Well, I'm gonna ignore that. I guess I had something wrong. Let's look at it one more time. So the first step here is I'm setting the direction. And I set the direction both on PB7 and PB5. Then I set PB6 low on the PB6 low, the Z axis here. Here I set PB4 low. I did my delay of 5 microseconds. Then I set PB6 high. There we go. And then PB4, that should be PB4 high, which is my y-axis. And I repeat. And you can see over here, I've got both motions moving simultaneously. Finally, I can come back and turn on my last port. To do that, I'm going to go ahead and open back up my other code just so I can recall the ports that I was setting. So for the x-axis, I needed a here. For the x-axis, I had a port H set it equal to I used the logical shift left because I was only doing one. That worked fine. So that's set. Six x-axis. And then I'm going to first set the bit low, port H, and equal with 0B. And it was on PH5. So 765432110. Set PV PH5 low x-axis. And then I'm going to port H or equal. I'm using or equal to set the bit I again. So 0B 765432110. So I'm going to set PH5 high to give my x-axis. All right, so again, it was directions. A little odd the way those were chosen, but there we go. I'm going to go ahead and send these. Okay, so I send them. Now I'm getting simultaneous contemporaneous motion on all three drives because I'm doing it right here in the real-time interrupt. Each time I call the real-time interrupt, I'm setting the ports correspondingly, allowing me to drive at the same time. Now, at this point, probably there's we'll stop here. Looking ahead, there's maybe then two things I'd want to do. Perhaps have each one move, well, three things actually. Right now, they're all moving the same amount. They're moving at the same time, but they're maybe moving the same amount, same speed. Might be nice to have different speeds. So I could make a if statement like this for each of the ports. They could be running at different speeds, and I'd still drop it in my real-time interrupt. That's kind of easy to see. Right now, they're all doing the same direct distance before a direction change. Again, I could make one of these corresponding to each axis. I'd have to do that. We could do that. And then the last step is I'm still using this bang, bang, linear velocity, not linear, constant velocity, but bang, bang control in changing my velocity. And that's greatly limiting the max speed that I can get. So that'd be the last thing I want to come back and look at. But thanks for your attention. I hope you got something out of this lecture.